by Jackie Locke.
Thank you. So thanks. This will be a talk on the dynamics of gradient descent, so it's a little bit different in flavor to the other talks so far. And this will be based on joint work with Rishi Sonthalia at Boston College and my advisor, Elizaveta Rebrova. So the main motivating question for the talk, which applies far more generally, is just the following. If we're given a particular problem, in our case it will be a regression, and we want to solve it using some kind of iterative algorithm, how can we understand the dynamics of the parameters that are learned by this algorithm? So in a picture, imagine what we would like ideally is being able to draw these curves, giving us the test error and the training error of this algorithm as a function of the number of epochs or passes through the entire data set without actually running the algorithm. So you could imagine this would be interesting in practice. You don't actually have to run it to see, for example, you want to stop early to minimize your test error rather than keep going to convergence. And in theory, if you had formulas for this, you could get a lot of precise answers to questions you might have. So that's not really possible for a lot of more complicated models and algorithms. So we're going to consider more specifically linear regression and more specifically a linear model. So our setup is like this. We're given features xi that are vectors, that are p-dimensional, and we're going to be trying to predict responses that are real numbers. And we want to minimize and solve kind of the least squares estimator, so empirical risk estimation. We'll assume the responses are linear in some underlying parameter, beta star, and we can allow it to be perturbed by some noise, which we'll assume to be independent. And it's kind of matrix theme, so the formula will be X is the matrix of vectors, it's n by p-dimensional, and our response will kind of be linear in this true underlying parameter we're trying to learn. Gradient descent, it's a very familiar algorithm. Every step, we just take a step in the negative gradient of our loss function. In this case, it's linear, so it takes this form. And the key parameter is the step size. So there's a lot of works. The key question is, how do you choose the step size, or how do you adaptively select it over time? We'll fix it to be a constant alpha throughout. Sorry about that. Yeah. And we'll study gradient descent for that. And just kind of a few words about why studying dynamics of gradient descent for linear models might be interesting. Kind of from a machine learning theory perspective, one of the key questions is to understand the implicit biases for algorithms used to train not linear models, but kind of more complicated models. So think of like neural networks. So linear models, one answer I think of that might be relevant to the kind of techniques that appear in this talk is that they demonstrate interesting behaviors observed empirically. So the first one is that kind of you have gradient descent and you want to understand its implicit regularization effects, and there are works kind of explaining that gradient descent for linear models acts as a shrinkage estimator. And that's kind of why it's similar effects to ridge regularization. There are works studying linear models showing kind of what are the benefits of overparameterization, the double descent phenomenon. You can kind of highlight that appears in linear models already. And also kind of line of work in machine learning showing that in certain regimes, complex models kind of are effectively the same as linear models. So here I'm kind of referring to works saying deep neural networks in the so-called neural tangent kernel regime, or they also call it lazy training regime. And one key idea is that the trajectory of the parameters being learned under gradient descent, or also gradient flow, which is just kind of we take the limit of the step size going to 0, is essentially governed by the eigenvalues, the spectrum of this sample covariance matrix of the features. So I'll denote it as W throughout the talk. It's just you take your features, X transpose X, and divide by the number of samples you have. So here will be a P by P kind of square matrix. And onto the kind of actual algorithm we're going to be thinking about, mini-batch gradient descent, which is also known as kind of stochastic gradient descent. We'll assume that our data is partitioned to capital B mini-batches throughout. And what I guess is the main thing we're studying is a model called random reshuffling. So you have your mini-batches, you want to go train your model, you randomly permute your data, or mini-batches in this case, and do mini-batch gradient descent of these capital B mini-batches in that order. That'll be one epoch, because it will be one pass through the entire data set. And then you randomly permute those mini batches. So here's denoted by tau, and you do it again. So that's very natural. It's very practical. So it's probably what you would do in practice, and also kind of effective. The main difficulty is that it's very difficult to analyze because you have much limited independence compared to if you sample a mini batch with replacement, because each mini batch is then independent and you have a lot of techniques to control the kind of behavior of the dynamics that emerge. So I did not mention here, but this kind of problem has been studied in the stochastic optimization literature, and what they show is that random reshuffling kind of does converge with a faster rate than kind of generic SGD with replacement for more general optimization problems than considered here. So the main question we'll look at is just what are the dynamics of the parameter that are learned after k epochs. And we'll look at specifically what's the mean iterate that is learned. So rather than kind of looking at the stochastic parameter, so that will involve kind of more stochastic processes, we'll look at the mean, which is then a concrete vector we can track, where the averaging is over the random permutations in each epoch. So just as a slide we have before the presentation of the main message is a few technical equations. With our setup, we've got capital B mini batches, and within each mini batch XB, it'll have its own sample covariance, denoted by capital WB here. What we're going to do is define for each mini batch a set of so-called modified mini batches. So it's just XB with a tilde on top, and what we're doing is we take each feature in each mini batch, or row in our notation, and multiply it by some matrix pi b. So pi b looks a bit abstract, but what it is, if we just ignore the expectation, is that it's accounting for the effect of all the other mini batches that appear before the current mini batch during the learning process, and then kind of like what's the learning that's done because those mini batches have appeared before it during the epoch. And then the expectation is because we're considering the mean iterate. So it's a kind of averaged analysis. So it's the average effect of all the other mini batches that kind of appear before it in a kind of temporal way. And from that, we define a so-called cross-covariance matrix between our features X and these modified features with a tilde, as we'll call it Z. So it's defined the same way as the sample covariance before, which is just X transpose X. But here we'll just have replace one of the X's with a tilde. Right, so one key observation is that if you kind of expand out the definition, up to first order in the step size, it'll be equal to W, which was the sample covariance I was talking about, which will be quite interesting. It's symmetric, so it's not apparent from the definition, but because we have the symmetric group that's involved, then we're kind of taking the expectation over that. And it's a non-commutative polynomial of the mini batch covariance matrices. So that's kind of a non-trivial thing to look at. And I guess to illustrate the more abstract definition, it's perhaps easier just to look at what they look like concretely in the two-batch case. So we fix b equals 2 and just plug in the formulas. So you can see x1 tilde is just x1 multiplied kind of by an identity matrix minus alpha times w2. So it looks like that. And perhaps the second thing is that z looks like this. The green term is equal to w. It's just up to scaling of the mini batches. And there's a second term which looks kind of funny. So it's kind of known as the anti-commutator of these two sample batch mini covariances. And it kind of hints at why random reshuffling is difficult, because it involves interactions between mini batches that already emerges in this most simple two-batch case. And so onto the main message, having constructed these definitions that look a little weird, we have, here's a formula for telling us beta k, that's the mean iterate after k epochs. We have a formula for what it looks like. Okay. So just to kind of digest this a bit, it doesn't really matter what is there. But the first term is kind of like, it tells you what's the bias of the parameter that is learned. You can imagine with a small step size, it's kind of shrinking, it's contracting, and it tends to 0. So it's kind of learning the signal. The second term corresponds to the variance. So you can imagine it's kind of a term that's growing, and it comes from learning the noise that is inherent in our model. So why this is interesting, if you do the same thing, you just do vanilla gradient descent, very familiar, you just kind of write down the equations, you will derive this equation for the equivalent dynamics. So this will appear in kind of the basic results in a textbook. And just to highlight the key point is that what's interesting is you just have basically the same evolution where you replace W with Z, so covariance matrix with this cross covariance involving some modified features, and also kind of a linear scaling rule, which relates to a rule used in practice, discovered empirically, but kind of interesting to see how it arises naturally. Perhaps not so surprising since everything is linear. So just to show in the picture, the blue curve is kind of, if you do full batch gradient descent, this is on some simulated Gaussian data, you can see a kind of difference, especially if you have larger step sizes. What's kind of interesting is if you send the step size to 0, the curves all look the same. And that is because they all correspond to the same continuous time dynamics, which is gradient flow. So it's kind of the random reshuffling leads to kind of dependencies between mini batches that is kind of more subtle because it kind of depends on the step size in this way. And just to illustrate it, at the other extreme, if you use much bigger step sizes, it's known that gradient descent can diverge, whereas mini batch can still converge if it's big, but not big enough compared to this, the spectrum of this cross covariance matrix Z. This slide basically says we have an abstract formula that doesn't really use the assumptions. This just tells you we can make more assumptions, such as looking at asymptotically. What is the effect of random reshuffling? If we assume that the true population covariance is sigma, what it's doing is that it's kind of causing a shrinkage effect on the eigenvalues. So if you stare at the formula, if you do the full batch gradient descent analysis, you get the same thing with just lambda I. In this case, you somehow get lambda I times something smaller than 1 for appropriate step sizes. So that's kind of the takeaway caused by kind of the dependencies caused by this process. Here's a picture kind of illustrating that. And what's kind of interesting here is that it's actually in the high dimensional regime. So this is actually computed numerically for the 2-batch case for Gaussian data. It's, if you're interested in random matrices, here's a kind of random matrix theory question. This was the formula for the Z, for the 2-batch case that I put earlier. I don't know an analytical formula for the spectral distribution of this. The sample covariance, the limit is the so-called Marchenko-Pasteur distribution. Because this involves the interactions between kind of independent random matrices, it's kind of difficult to say what the answer is. But you can plot it numerically and you can see the shrinkage. So yeah, just to conclude, this work shows there's kind of an interesting analogy between if you do random reshuffling, for linear models specifically, there is a kind of subtle dependence effect on the dynamics caused by the dependencies between mini batches. We can quantify it more concretely as a kind of shrinkage effect on the eigenvalues. And I guess more generally, because this is just a difficult problem to study for more complicated or realistic training algorithms, what is the effect of kind of random reshuffling more generally, which is a very broad question. And that brings me to the end of my talk. Thank you.
And there's time for a question or two. Yeah, so can you maybe say something about that random matrix theory question a little bit? So it's a Wishart, you said it was a Wishart matrix?
Yeah, so in this case I assume X is Gaussian, so the theta X is Gaussian. So a W, which is X transpose X divided by N, is known as a Wishart matrix.
Yeah.
So this green thing, it's P by P. So here we're into the high dimensional regime, which means P tends to infinity. It's a proportional regime, means P, the number of parameters, divided by the sample size, tends to a finite limit.
Yeah.
So that's well known. So the point is you can evaluate all the expressions before under this high dimensional limit for gradient descent. In the random reshuffling case, I guess the picture, okay, if you imagine replacing everything with Z,
Yeah.
I guess you have this matrix.
Yeah.
What is there kind of an analytical understanding
Yeah,
of
right. Oh,
what is the limiting spectrum of this?
Interesting. Okay. Okay. Any more questions? Okay, let's thank all the speakers of this session.